Hello everyone, my name is Adithya Keel and I am here with my teammates Apoorv Anand and Aman Tulsiyan. We are 5th semester students studying in the BMS College of Engineering in the AML department, and today we are going to be explaining the whale optimization algorithm in nature-inspired computing. This video consists of the nature-inspired computing definition and about whales, and we also have the whale behavior in the algorithm followed by the mathematical model and the coefficient vectors and their mechanism. This video will also include a numerical example to explain the working of the whale optimization algorithm, followed by the algorithm itself and the flowchart. Firstly, what are nature-inspired computing algorithms? Nature-inspired computing is a branch of computational intelligence where we design algorithms by observing natural processes and behaviors. NIC methods copy ideas like genetic adaptation, swarm intelligence, and animal movement patterns to solve difficult optimization problems. These methods are powerful because they are flexible, self-organizing, and often escape local optima better than traditional mathematical techniques. Among many species studied, humpback whales are unique due to their advanced communication and cooperative hunting strategies. Their bubble net feeding method inspired the whale optimization algorithm, which we are going to see today. The whale optimization algorithm. The whale optimization algorithm, or the WOA, is a meta-heuristic inspired by how humpback whales trap and they capture prey. It mainly models two key behaviors. The first one is the shrinking encirclement, which is the shrinking circular movement, and the second is the spiral attack, which is the spiral movement during the bubble net feeding. These two actions represent the core search operations in the whale optimization algorithm. Firstly, the shrinking encirclement stimulates the local exploitation around the best solution, and the spiral attack stimulates a smooth, curved approach toward the target. Whale optimization algorithm also includes a random exploration phase which represents whales searching across large ocean regions. This balance between exploration and exploitation helps the algorithm effectively search the solution space. Now coming to the main feeding strategy, which is the humpback whale hunting strategy, which is called the bubble net feeding. Humpback whales use a very coordinated hunting technique called bubble net feeding. A group of whales dive deep below a school of fish and then swim towards a circular path while blowing bubbles. These bubbles create a cylindrical or circular net that traps the prey and restricts their movement. While rising, the whales follow shrinking circular paths, tightening the bubble net as they move closer to the prey. This coordinated movement is one of the key inspirations for the encircling mechanisms in the whale optimization algorithm. They also exhibit a distinctive logarithmic spiral movement. These waste whales they follow spiral trajectory. This is often described as a logarithmic spiral. It helps the whales push the fish toward the center of the bubble net. So, together with both of these, the shrinking circles and the upward spiral motion form an efficient prey trapping mechanism. These natural movement patterns are directly translated into the mathematical model of the whale optimization algorithm. Here we have a small animation to show the bubble net feeding strategy. Firstly, the whales target and they find the prey, which might be a school of fish hunting, and then they dive down deep below the prey. And then, as they move towards the prey, they uh, they release bubble nets which in circular patterns so as to restrict the prey themselves, and they move in spiral patterns which form a cylindrical shape and they move towards the prey, and they hunt the prey in the bubble net feeding strategy. Now coming to the mathematical model, the whale optimization algorithm uses translates humpback whale hunting behavior into three core mathematical operators. The first mathematical operator in whale optimization algorithm is the encircling prey, which represents exploitation. Whale optimization algorithm assumes that the best solution found so far is the prey and all whales move towards it. This is modeled using the formula xt plus 1 is equal to x star minus a into c into x star minus xt, where c into x star minus xt is also called as d, is the d which is the distance between a whale and the prey, where and x star is the best solution found so far, and a and c are the coefficient vectors that control movement intensity. As iteration progresses, the value of A decreases gradually, which causes the whales to shrink their encircling movement and converge toward the best solution. The second operator is the spiral attack, which models the whale's logarithmic spiral upward movement. This creates a curved, non-linear path toward the target solution. This position update equation for this is xt plus 1 is equal to d into e b t to the power bl into cos 2 pi l plus x star. Here d dash is equal to x star minus xt. B controls the shape of the spiral and L is a random value between minus 1 and 1. This formula combines the exponential tightening with the rotational motion, giving the smooth spiral convergence toward the target. The third operator models exploration. When the value of a mod a is greater than 1, whales stop following the best solution and instead move around a randomly selected whale. This is given by x t plus 1 is equal to x random value minus a multiplied by c into x random minus xt, which is d. The overall is d. This mechanism helps the algorithm explore new areas, maintain diversity, and avoid getting stuck in local minima. It ensures that the search does not overly focus on one region too early. Now, my teammate Aman will be continuing the presentation by explaining the coefficient vectors in the whale optimization algorithm.
Hello, hi. I will be continuing the explanation by talking about the coefficient vectors of the whale optimization algorithm. Starting from this page, we discuss one of the most important control mechanisms in the whale optimization algorithm, the coefficient vectors A and C. These two vectors decide on how each whale moves in the search space and how the algorithm balances exploration and exploitation. Let's start with A. The vector A directly influences whether a whale should move towards the best solution or away from it. If the best value of A, meaning modulus of A, is less than 1, the whale believes it is close to the prey, so it performs exploitation, tightening its movement towards the best solution found so far. But if modulus of A is greater than 1, then the whale performs exploration, meaning it moves away from the best whale and looks for new, potentially better areas in the search space. This prevents the algorithm from getting stuck too early. The interesting part is how A changes over time. There is a parameter called small a, which starts at 2 and decreases linearly to 0 as the iterations go on. Because of this, early in the algorithm, modulus of A is usually greater than 1, which encourages wide exploration. But as the algorithm moves forward and gradually shrinks, A also shrinks, and that pushes the whales towards more focused exploitation. This gradual transition is what makes whale optimization algorithm both stable and efficient. Now, because it starts wide and ends sharp. Let's go to C. This vector adds randomness. It controls how strongly a whale is attracted or repelled from another whale or the current best solution. C helps introduce diversity in the movement, making sure the whales don't follow the exact same path. Together, A and C act like steering wheel and accelerator of the algorithm. Moving on to the next page, we have the complete algorithm workflow. It starts by initializing a whale population, meaning we randomly generate several possible solutions. Then we calculate the fitness of each whale based on the objective function. The whale with the best fitness value becomes the temporary prey. Once we know the best whale, each whale chooses one of the three movements strategies. It can encircle the best solution, mimicking the shrinking circular bubble net behavior. It can follow a spiral path towards the best whale, representing the logarithmic spiral movement, or it can explore randomly, which helps the algorithm escape local minima and discover new promising areas. These steps repeat until a stopping condition is reached, usually a maximum number of iterations. Where optimization algorithm stands out because it is simple, lightweight, and extremely easy to implement, yet surprisingly powerful. Now let's go ahead and see the numerical examples. This example clearly states the changing of positions by applying the mathematical equations. The page shows initial positions and explains how each whale updates its position based on A and C and the movement strategy chosen. After even the first application of the formulas, you can see the whale shifting closer to the better solutions. This page continues the numerical example where the intermediate steps are shown in which the whale 1 is going towards the exploitation path encircling the best whale. Each whale moves slightly differently depending on the coefficient and the vectors chosen. They can choose either encirclement, spiral movement, or random exploration. Here, the whale 1 is encircling the best solution, which is exploitation. Then we go towards the whale 2, which is also the best whale. It is also going to the strategy of encircling. Whale optimization algorithm can sometimes move a bit away and then come back. Now we go to the whale 3, which performs exploration and then moves relative to a random whale. Now we are getting the flowchart of all the positions of all the whales after iteration 1. This is simple but powerful demonstration. Even just after one iteration, the whales have clearly moved closer to the prey, being the best possible solution. This proves that the algorithm begins optimizing right from the start, adjusting positions in a meaningful way. Finally, this page gives us the flowchart of the whale optimization algorithm. This flowchart visually summarizes everything. We start the algorithm, initialize the whale population, evaluate the fitness, update each whale using A, C, and a random parameter P, choose between spiral, encircle, and exploration, check whether the termination condition is met, and finally return the best solution. Flowchart clearly shows how the algorithm repeatedly cycles between exploration and exploitation until it converges to an optimal solution. Now I'd like my friend Apoorv to take over and explain the rest of the file.
Hello everyone, my name is Apoorv and I'm going to take implementation and visualization part of the whale optimization algorithm. First we see what is Healy test function. It is a custom functions that create a landscape full of smooth hills. It contains multiple small local maxima and minima and it's used to observe how the algorithm performs in the earlier exploration stage. The wave the whale optimization algorithms explore this landscape by moving across these hills, and we can clearly see in the animation how it's began identifying the promising regions while still maintaining movements across the search space. Like this, the agents began moving towards the area with the higher fitness values. This shows how algorithm balance exploration and exploitation in a smooth landscape. Next, we see what is a forest test function. The forest test resembles a high, rigid terrain with many tall and closely spaced peak like trees in the dense forest. It is highly multimodal, meaning that there are many local optima which can make optimizations very challenging. This test helps evaluate whether an algorithms can avoid getting trapped in the local minima. Here is the visual representation of the forest test function. So here we can see in the animation that the terrain is extremely rugged and the algorithm maintains diversity to escape local optima. The visualization shows how whale optimization algorithms continues to search new area instead of setting too early, demonstrating it robusting in complex environment. Now next we see Ackley test function. The next function is the Ackley test function, which is one of the most widely used benchmark function in optimization. It has a large number of local minima scattered across the landscape and a single global minima at the center. This makes it ideal for testing whether an optimization algorithms can consistently reach the true global optimum. Here's the visual representation of Ackley test function. Initially, the whales explore across the entire surfaces. As iteration progressed, the population began converging towards the global minima near the center. This visualization highlights whale optimization algorithm capability to converge quickly even in the complex landscape. Next, we see megacity test function. It is another custom designed visualization function. This function contains very tall and sharp peaks similar to skyscrapers in the cities. Because of this high contrast between peaks and values, the search space becomes extremely challenging to navigate. This test is used to analyze how well Whale's optimization algorithms perform fine-tuned exploitation and how its approach sharp optimum. Here it is the visualization. The whales must precisely identify the tall peaks while still avoiding misleading points. The visualization clearly show how whale optimization algorithm gradually moves upwards towards the sharp global optimum and demonstrate its strong exploration ability. Now let's move to the advantages of the whale optimization algorithm. First, we discuss what are different types of advantages of whale optimization technique. First is simple and easy to implement. With only a few mathematical operations, whale optimization algorithm is very straightforward to code and adapt. Second one is minimum parameter tuning. It uses only a few good control parameters, make it stable and less complex. First, the third one is good balance between exploration and exploitation. The fourth one is effective for multi-models and non-linear problems. The whale optimization works well even when there are many local minima. The fifth one is fast conversion. Its movement strategies helps quickly guides the population towards the promising region. The next we see what is the limitation of whale optimization algorithm. Despite its strength, whale optimization had some limitation. The first is susceptibility to local minima. In extremely rugged landscape, the algorithm may still get stuck. It is second one is it is sensitive to parameter A. If the parameter is not described properly, exploration or convergence may weaken. The third one is not it doesn't guarantee us optimal global or like most optimization. It offer near optimum solution but not guarantee optimus. The fourth one is slower in high dimensional problem. As dimension increases, its movements pattern become less effective. The fifth one is performance varies by performance type, by problem type. Whale optimization works better for continuous optimization than discrete one without modification. Now let's we see what is the application of whale optimization algorithm. The first is feature selection in machine learning. Selecting the most relevant features improve accuracy and reduce computation in machine learning. So second, we see engineering design optimization used across mechanical, electrical, structural field for parameter optimization. The third we see is scheduling and resource allocation. Helps solve hard problems such as job scheduling and load balancing. The fourth we see is image processing, useful for segmentation, clustering, and threshold optimization. Now, at last, with this, we conclude the presentation and thank you for watching. And if you have any questions, we will be happy to answer the questions. Thank you very much.